Hi everyone, welcome to week 7. Today we will be going over chapter 6 questions, and we will be going over the periodic trends just as we did last week, as well as bonding and some of the electron configuration with some of different ions and comparing certain sizes versus how many protons they have and electrons and what that does to their electronegativity and things like that. So let's get into it. So if you can see my screen, perfect. Just pull this up really quick. Okay, so we are going over question 56, and this question is: which atom has the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d7, and 4s2. Okay, so whenever we see electron configuration such as this, we can always look at the last term here, and that can tell us what atom this has on the periodic table, because this is the last place. So the atom is going to be on the last term that is written on the electron configuration. So this is 4s2. So when we go to the periodic table, 4s2 will be in the fourth row, 1, 2, 3, 4, and it will be s2. So s2 is the first two columns here. That's the S category. And since it's s2, it's the second one in the S, so that will be, let me just get rid of all of these highlights here. It'll be calcium, because that is in the 4s2 category. And all of the other places are filled up completely. So yeah, that is what that will look like. So that is the answer. It is calcium. And for 62, let's move on to this question. It says, in one area of Australia, the cattle did not thrive despite the presence of suitable forage. An investigation showed the cause to be the absence of sufficient cobalt. Let me look at the chat here. It was just fine before I signed in. Now it is going in and out. Okay. Is it still going in and out? Okay, just let me know if it's going in and out again. I could try to see what the problem is with that. If there aren't any more issues, I can continue. Okay. Just let me know. Okay, so in this question, nope, still having trouble. Okay. Did you say it's going in and out, the audio? I can try to, let's see here. Let me just reset this really quickly. Okay, is this better a little bit? Hopefully the audio is not going in and out anymore. I'll just read the question and see if it's still going in and out. Okay, in one area of Australia, is this okay? Okay, I'll just continue. You let me know. Hopefully that might have changed it a little bit. Okay, let's just move on. Okay, so the cattle did not thrive despite the presence of suitable forage. An investigation showed the cause to be the absence of sufficient cobalt in the soil. Cobalt forms cations in two oxidation states, cobalt 2+ and cobalt 3+. Write the electron construction or structure of the cations. Okay, so first of all, we're trying to find the electron configuration of 2+ and 3+, but it would be really, really helpful for us to look at not the ion version of cobalt. So let's first write down the ion, or not the ion configuration of cobalt, and then we can see for the cations 2+ and 3+, where we are actually removing certain terms of the electron configuration. Are you having trouble? I'm fine. Hopefully the audio I'm okay. Are you having trouble hearing me? That's the question. Okay. Yeah, so for looking for the cobalt configuration, we can find it on the periodic table. We're not using Zoom. The platform for this is using Twitch for the streaming. Okay, so cobalt is right here on the periodic table, and so this is in the 4th row. So for the configuration, it's going to be filled up all 3 rows before it, so we can write down all of those. So it'll be 1s2, 2s2. Let me write it down so that you can see it a little bit better. No, we cannot stick to answer your question, PSU Learning Center wants this to be through Twitch, so it's easy to live stream. And then I'm posting this to YouTube, so you can always watch this back as well. Okay, so cobalt, it's 1s2, 2s2, 2p6, and 3s2, and 3p6. So that goes all the way up to the 3rd row, and since cobalt goes into the 4th row, it fills up 4s2, and it goes to 3d, and it's 1, 2, 3, 4, 5, 6, 7. So it's the 7th one in the D category. So what that would look like is 3p6, and then it'll be 4s2, since it fills that up, and then 3d7. So that's the configuration of just cobalt. So considering the configuration of cobalt, now we're going to find the cations of those oxidation states of cobalt 2+ and 3+. So cobalt 2+, what will happen is whenever we have an ion or a cation and you are removing the electrons, it'll be removed from the lowest energy state, and so in cobalt here, it'll be removed from 4s2. So since it's a 2+, it loses 2 electrons. It gives it away. So this term right here will be removed. So cobalt 2+ will be 1s2, 2s2, 2p6, 3s2, 3p6, and 3d7. And to kind of revise what I just said, it removes it from the lowest energy state, but it's the nearest lowest energy state, because the D category has a bit of a higher energy state, so it's harder to remove the electrons in that category. So that's why it goes back to the nearest one, and that's the S category, and that's easier to remove the electrons. And so moving on to cobalt 3+, it will remove 1 more electron than the previous cation. And so doing that, we need to remove it from also the nearest lowest energy state. And so working from the configuration that we just wrote, it'll take it from the D7 or the D category, because the D category has a lower energy than the P category. So that'll be removed from there, so it'll look like very similar to cobalt 2 plus, but 1s2, 2s2, 2p6, 3s2, 3p6, and 3d6 as well. So that's what that looks like. It's always good to know the original configuration and then write down the cations and look at the lowest energy categories, and then it'll become kind of easier to follow in that way. Oh, I'm sorry. So it's still going in and out. Let me see if I can see what you are hearing on your end. In one area of Australia, I'm just practicing to see what it sounds like. In one area of Australia, I'm just practicing to see what it sounds like. So it looks like it's fine on my end. I'm just doing this to see what it sounds like on Twitch on my phone. So it seems to be okay. Maybe it might be on your end. Let me know if it's still going in and out. It still sounds fine. So maybe the audio is just maybe a bit quieter. I can talk a little bit louder. Yeah, just let me know when you can. Okay, so moving on to question 68. Based on their position in the periodic table, predict which has the largest atomic. I think I was supposed to write radius here. Yes. And so the radiuses that we are working with are going to be lithium, Rb, nitrogen, fluorine, and iodine. Okay, these are going to be the atoms that we are working with. And so let's look at what that looks like on the periodic table. Okay, so let's find those on there. So getting rid of all of these marks here. Let's find lithium. So lithium is one of the selected ones. So lithium is right here. So there's lithium. Rb should be around in the middle here. Yes, oh, it's right here in the same column. And then nitrogen, as well as fluorine, as well as iodine. Okay, so these are the 5 atoms that we are working with. So whenever we are trying to find the atomic radius, we have to correlate that with the electronegativity. And if it has a stronger electronegativity, then it is able to pull their electrons closer to the nucleus, and that makes it smaller. So whenever it has more electrons moving to the right of the periodic table, it is going to become smaller. So working from that, and also whenever it has, the least amount of just stuff, it has the least amount of protons, least amount of neutrons, and protons, it's going to be smaller as well because it has less in the atom. So whenever you're moving across and also up at the same time, so kind of a diagonal upwards motion, that is going to result in general the smallest radius size of these atoms. So considering how that works, when we are working with the first row here with lithium, nitrogen, and fluorine, these are going to be smaller than the other 2 atoms we are working with, the rubidium and iodine, because these are larger atoms. They have more protons, more neutrons, more electrons, more of everything. Yeah, so the top row here, lithium, nitrogen, and fluorine, is going to be smaller than rubidium and iodine. And of the row of lithium, nitrogen, and fluorine, fluorine is going to be the smallest of everything, following nitrogen and following lithium, because fluorine has more electrons considerably, and it has 7 in its valence orbital, and so because it has 7 valence electrons, then it can pull closer to the nucleus because it's positively charged, and the electrons are negatively charged, so they're going to be very attracted to one one another, and so fluorine is going to be smaller than nitrogen and lithium. So let's write that down. Let's go back to the question here. So the smallest moving down to the largest. So that's the order I'm going to be writing the atoms in. So far we talked about the 3 atoms. So this is going to be the smallest of fluorine, and then it's going to be nitrogen and lithium. And so let's go back and look at rubidium and iodine. And so just as we talked about before, when we move upwards and to the right, it's going to be the smaller atom. And so iodine is much farther. It's all the way across, has 7 valence electrons, and rubidium has 1 valence electron. So iodine is going to be smaller than rubidium. And so that is what we have for the rest of our atom sizes here. So it's going to be fluorine, nitrogen, lithium, iodine, and rubidium. So 1, 2, 3, 4, 5. So that is our final answer for this problem. Yeah, so let's move on to 72. And it is, the question is, based on their positions in the periodic table, rank the following atoms in order of increasing first ionization energy: magnesium, oxygen, sulfur, and silicon. Okay, so let's look at these on the periodic table. And let's discuss this first. So electronegativity is very similar with ionization energy. It wants to, ionization energy has to do with giving up their ions, and how easily they're able to have that. And so when they have more ionization energy, that means they're not going to give up their electrons as much. So we have 4 atoms here that we're working with. Let's first find them on the periodic table and look at where they are located, and then we can make that decision afterwards. Okay, so, oopsie. We have oxygen, and we have sulfur, and we have silicon, and we have magnesium. Okay, so considering all of these, oxygen seems to be the number 1 rank of ionization energy out of these 4, because it is closer to the top and to the right of the trend of the ionization energy, because it has the least amount of electrons, so it's going to hold on. It has the least amount of protons, neutrons, and electrons out of all 4 of these atoms, so it's going to want to hold on to everything even more so, and especially since it has 6 valence electrons as well. So oxygen is the first one, and then using the same pattern here, sulfur is going to be the second, because it is also furthest to the right, and these 3 here are on the same row. And so because of that, we're going to be looking at the farthest to the right is going to have the first amount of ionization energy. And because of that, sulfur is going to be the second one in ionization energy, and then silicon, and then magnesium, because of following the left and right and up and down pattern. Okay. So let's write that down. We said oxygen, sulfur, silicon, and magnesium. So those are the 4 atoms that we are working with in that order. Okay, so let's move on to question 74. It has a question of atoms of which group in the periodic table have a valence shell electron configuration of ns2. Okay, so the configuration is only ns2, and we know that since we have an S2 category on the periodic table is going to be the second column, and that is going to be the alkaline metals. So that's going to be right here, because this whole section is the S category, and S2 means it's the second one in the category, or the second column, and that is going to be the alkaline metals. So that is the answer to that. NS2 is the alkaline metal group. Okay, let's move on to question 78. List the following ions in order of increasing radius: lithium plus, magnesium 2 plus, bromine minus, and Te2 minus. I forgot what that atom is pronounced, but it's Te. Yeah, so let's list the order of increasing radius. And so this gets a little bit more tricky because charges can really affect how small something is, and that is more important than sometimes the row number, and I'll show you what that looks like. But let's first look at where all 4 of these ions are located on the periodic table, and then let's look at their radiuses. Okay, so we have lithium right here, and we have magnesium. We have bromine, and we have Te. Let's see if I can find it. Te. It's probably right in front of me. There it is. Te 2 minus. Okay, so considering all of these, the smallest atomic radius here is not something you would expect at first because, you know, considering what we were talking about, farthest up and to the right is going to have the smallest radius, yes, in general. But for some of these ions, it's very, very close in radius, and sometimes one thing gets prioritized for radius rules than others. So when I was talking about row versus charges, sometimes the charge matters more than the row it's in. And so lithium here is in the second row, so you would think it would be smaller than the third row of magnesium. But because magnesium has a 2 plus charge, it's going to have a smaller radius because it has more electrons, so it's going to be pulled more towards the nucleus and creating a smaller radius size. And so magnesium is actually the smallest, and then it is followed by lithium, the lithium ion. So those are those two. And then now we're looking at bromine, and it says here the Te is tellurium. So tellurium and bromine. And so because bromine is in the 4th row and tellurium is in the 5th row, tellurium is going to be larger because of that fact. And because bromine has a different charge than tellurium here, it's a different kind of relationship between these two atoms versus the other two, because one has less of an electron charge. It's +1 versus a +2, so that's different than a minus and a 2 minus, and especially because these atoms are so much larger, and that can really have an effect on the radius size. So here, let's write this down where we have our question. The smallest atom or the atomic radius is going to be the magnesium 2 plus, and then it's going to be followed by lithium plus, and then bromine minus, and then tellurium 2 minus. And so because the bromine has a minus and the tellurium has a 2 minus, because it only is 1 electron away from being complete, the bromine has a lot of electrons, more so than the tellurium here, and so it's going to be pulled more towards the nucleus, and so that's why it's going to be smaller than the tellurium. So it's just keeping in mind the charges sometimes really do matter with the different, if it's just one row off from each other, the charges matter more. Okay, so let's move on to the next question. So the next question states, which of the following atoms and ions is/are isoelectronic with sulfur 2+, silicon 4+, chlorine 3+, argon, As, I think that's arsenide, something like that, and then silicon, neutral, not an ion, and then aluminum 3+. Okay, so let's look at all of these. So let's first find them on the periodic table to make our life a little bit easier. But actually before we find them on the periodic table, let's actually identify what isoelectronic is, and then we can see what we're actually looking for and what we're answering in the first place. So isoelectronic means it is a ground state electron configuration, or its ground state electron configuration are the same. Okay, so for all of these that we see here, we are actually going to find the ground state version of all of these ions here. And so when we look at that, then we can compare which ones are pairings, basically. So if it has the same ground state configuration, then it's those two atoms, or how many ever atoms, they are isoelectronic because of that. Okay, so let's first look at silicon 2+. So silicon 2+ is going to be right here. And so that's where that is. Let me just make sure I'm doing this correctly. Yes. Okay. So that's where sulfur is, and let's look at where silicon is. So silicon is right here. And then for chlorine, chlorine is right over here. Actually, let's do different colors so we can keep track of everything. So this is chlorine. This is sulfur. This is silicon. Let's just ignore all these colors for now. Okay. We have sulfur, silicon, chlorine, argon. Let's find another color. Argon. Argon is right over here. And then As3+. And so that will be right over here. Here's As. And then silicon is, we already have that. And then aluminum 3+. And aluminum is right over here. Let's do a different color. Okay. So we have to find the original configurations of these. So that means we're going to have to get rid of these charges to find out what it was before, if that makes sense. Let's look at the sulfur 2+. So sulfur 2+, will have to, it lost 2 electrons, so that means we have to get back to sulfur, and so sulfur will be at right here. It'll go back 2 places, so it'll actually have a charge of silicon here. And so for the aluminum loses 3 because it's aluminum 3+, so it lost 3 electrons, so we need to go back 3 places. So the aluminum goes back 1 place to magnesium, another place is sodium, and then 1 more to neon. So the aluminum will actually go to neon here. So that's what that is. So let's write that down. So that's reconfiguring everything. The sulfur actually went to here. and the aluminum went to the neon. So that's what we have for the colors and everything, for, making sure we're consistent. Okay, so we have sulfur, we have the aluminum, so we got rid of these. And so for silicon, the 4 plus ion, so since it's right here that we have highlighted in the orange, since it gained 4 electrons, we have to remove those 4 electrons. It lost 4 electrons, so we have to put them back. So we have to go back. So that's 1, 2, 3, 4. So it actually goes back to neon. And so because the silicon actually, the silicon 4 plus and the aluminum 3 plus, they went back to the same ground state configuration, those two will be isoelectronic. So the Al 3 plus and silicon 4 plus are isoelectronic. So those two are, yeah. So let's move on to the others here. And so we got done with those 3. Let's move on to the chlorine 3 plus. So the chlorine 3 plus is highlighted in the purple right here. And so it'll gain, or since it lost 3 electrons, we have to go back and get those back. So that'll be in the place of phosphorus. And so that is what that looks like for the chlorine. And so now let's look at the silicon 2 plus. So the silicon 2 plus, silicon is right here. So we will actually need to, the sulfur 2 plus. My bad. Yeah, the sulfur 2 plus is right here. And so since the sulfur will have to move 2 places, we'll have to see what that will look like. So that will go back 2 places with the silicon. Actually, let me look at this really quickly to make sure it's consistent with what the answers are. Okay, and so because of the sulfur and the way the sulfur 2 plus works and the chlorine 3 plus, it's going to be similar to where it will end up being at, because the sulfur and the chlorine, so the sulfur is 2 plus and the chlorine is 3 plus, and so since the chlorine is 1 more to the right of chlorine, it'll have the same ground state electron configuration. And so because of that, these two are also isoelectronic, just as the aluminum and silicon are. And I know this is tricky to kind of figure out, but you just really have to be consistent with where you're placing these original marks on your periodic table, and then where they go to, depending on their ground state charges. So the aluminum and silicon are isoelectronic, as well as the chlorine 3 plus and sulfur 2 plus. Are also isoelectronic. And the ones that are not here, so the argon is left by itself because that has the same, or it doesn't have any shared ground state configuration with anything else. So the argon is not isoelectronic here, as well as arsenic, or I believe that's arsenic. Yeah, the arsenic does not have any shared charge with anything. And so when you go back 3 places, 1, 2, 3, it ends up at calcium. Nothing is shared with calcium. And argon, it's not an ion here. It's a halogen, so it doesn't have any charge. So it's just alone in this place. So nothing is shared there. But yeah, so the argon is not. The arsenic 3 plus is not. And I believe one more is not as well. Which one is it? Yeah, and then the silicon, just as it is not as well. So the silicon with no charge is not isoelectronic. Yeah, so those are all of these atoms and their ground state configuration and which ones they are paired to. Let me know if you want me to go over anything again. It's kind of tricky to go over what configurations they end up being in and what they share with. But yeah, let's move on. Okay, so let's move on to question 84. The question is the ionic radii of the ions sulfur 2 minus, chlorine minus, and that is potassium plus, are 184, 181, 138 picometers respectively. Explain why these ions have different sizes even though they contain the same number of electrons. Okay, so let's first find them on the periodic table, and then it will be easier. Okay, so we have sulfur here, and then we have chlorine, and then we have potassium right here. Oopsie. And we have potassium. And so since they all, so the sulfur is a 2 minus, so it'll gain 2 electrons, so it'll go to argon. And then chlorine, it'll gain a minus charge and it'll go to argon as well, and then potassium will also go to argon as well. And it's because of its configuration as well. Okay, so because of these different places on the periodic table, we have to understand the trends that are in place, such as the electronegativity and also the amount of protons or electrons or the charges that they have. So using all 4 of those, or at least all of those patterns that we know about atoms, then we can explain why these have different radii even though they have they're going in the same place, or they end up in the same place. Okay, so because potassium is the smallest here, right? So let's first write that down. So the potassium is the smallest, and then it's chlorine minus, and then it's sulfur 2 minus. And so when we look at the sulfur and the chlorine, this makes sense as to why the chlorine is going to be smaller than sulfur. It's right next to each other. It's the same row. It only has a difference in one value of a charge, so minus versus a 2 minus. And so because the chlorine has a minus, and because it's very, very close to becoming a halogen, becoming a complete atom in its valence shell, it is going to have a stronger pull because it has 7 valence electrons versus 6 for the sulfur 2 minus. And so because of that, it has, like I said, it has a stronger pull towards the nucleus, so it's going to have a smaller radius because of that. So that is the reason why the chlorine is going to be smaller than the sulfur here. But then when we look at the potassium, you would at first think, like when I was working through these problems myself, I thought that the potassium, I was wondering why it was going to be smaller in the first place than the others two, because they're actually in a row down, because it's in the 4th row versus the 3rd row for the sulfur and the chlorine. But there is a reason why it is smaller, and the reason why is because it has more protons in the first place. So the potassium has 19 protons, and the chlorine has 17. Sulfur has 16. And so because it has more protons in its nucleus in the first place, and because it'll end up in the same place, the argon here, because of that basis, then that means it'll have a stronger pull to the nucleus because it has more protons, it has more positive charge, so it'll attract the electrons more, creating a smaller nucleus. And not only is losing electrons, it's more favorable because the potassium would need to lose an electron because it's a +1 charge, and the other two have to actually gain electrons because they're minus charges. And so because of that basis, then gaining electrons in the first place, yes, it can create a smaller radius because, more negative, more positive charge, and, it's going to squeeze really tightly towards each other. But there's also a phenomenon of electron-electron repulsion in the orbitals itself. So there's two kind of theories going on here when you have electron-electron repulsion, but also gaining electrons can also bring it closer to the nucleus. But all that being said, because potassium has more protons, and because it's going to be losing an electron, that is going to be more favorable, and that's going to create a smaller radius. So that is the reason why potassium is the smallest of all of the ions versus the chlorine and the sulfur. So that is all of the questions I have today. Hopefully this cleared some of the configuration questions you have and some of the trends of how atoms work and how their sizes can change versus, how much stuff they have, how many electrons or protons and the like. So let me know if you have any questions in the chat, and if not, I will see you all next week. Hopefully you have a great weekend, and your classes are going super well.